Is a rocky planet brighter, or a gas giant brighter? Whether we're talking about the apparent brightness, visual magnitude we see, or the planet's ability to reflect light, its albedo. First, let's look at our own solar system. The brightest planet has to be Venus, Earth's neighbor. As a rocky planet, Venus is extremely conspicuous in the night sky, even brighter than many stars. Calling it the brightest star in the night sky is accurate, aside from the sun and moon. However, the brightest planet in our solar system being a rocky planet doesn't mean it's the same outside the solar system. Can you imagine? In the universe, there is such a planet, wrapped in clouds of metallic vapor, where it even rains titanium. What would such a world be like? First, let's understand a basic principle. Just like the moon's light is actually reflected sunlight, planets themselves do not emit light, so the brightness we see from planets comes entirely from reflecting the light of their host star. The moon appears bright, largely because it's so close to Earth, not because its ability to reflect light is particularly strong. The moon's albedo is actually very low, only about 10%. That means, of the sunlight hitting the moon's surface, only 10% gets reflected back. Among the 8 planets in the solar system, the one with the weakest reflection ability is Mercury. Like the moon, it has no atmosphere, and its albedo is less than 9%. In contrast, other planets with atmospheres have decent reflection abilities. For example, Earth's albedo is about 30%. As for gas giants, like Jupiter and Saturn, Jupiter's albedo can reach about 50%, which is pretty good. But the most impressive is Venus. Venus is so bright, thanks to its thick atmosphere and the unique sulfuric acid clouds within it. These structures can reflect most of the sunlight back, giving it an albedo of 76%. So, besides the sun and moon, Venus is the brightest celestial object in the sky. This is undisputed within the solar system. Actually, for a planet to be conspicuous in the universe, having strong reflectivity alone isn't enough. It also needs to be very close to its host star. Take Venus for example. It not only crushes other planets in albedo, but it's also very close to the sun. Only 0.72 astronomical units, AU. 1 AU is the distance from Earth to the sun. In the solar system, it's only a bit farther than Mercury, because it's both close and reflective. It's so bright. Following this logic, the brightest planets outside our solar system most likely also need to be very close to their host stars. Astronomers have actually found such a planet. In 2019, they found an extremely rare planet orbiting a star named LTT 9779, located 264 light-years from Earth. The planet is designated LTT 9779b through transit method observations. Observing the brightness change when the planet passes in front of its star, analysis showed this planet is astonishingly bright, with an albedo reaching 80%, even higher than Venus. And, just as expected, it is extremely close to its host star, only 1/42nd the distance of Venus from the Sun. At such a close distance, coupled with such strong reflectivity, imagine how bright it must be. This planet is a gas giant, with a mass about 29 times that of Earth, and a radius 4.6 times Earth's. Astronomers classify it as a Neptune-like object. However, what makes it rare is not its high albedo, nor its Neptune-like identity. After all, about 1/3 of confirmed exoplanets are Neptune-like objects. What's truly special is that, as a Neptune-like object, it orbits its host star extremely closely. Common sense suggests it simply shouldn't exist in this location. Why do we say that? Typically, planets orbiting right next to their star are either huge gas giants like hot Jupiters, which have strong gravity to hold onto their atmospheres, or rocky planets roughly Earth-sized, which have little atmosphere, so even if stellar radiation blows it away, it doesn't matter much. If a medium-sized gas giant like a Neptune-like planet gets this close to its star, very soon, say within a year, figuratively meaning a short astronomical timescale, its outer atmosphere would be stripped clean by the star's high temperature and radiation, leaving behind only a small solid core. This is especially true around young stars, as young stars typically have stronger radiation. This planet's host star is similar in size to the Sun, also a G-type main sequence star, but much younger. The Sun is 4.6 billion years old, a middle-aged star, while this star is less than 2 billion years old, a young lad. Theoretically, such a young star should have fierce radiation, and the hydrogen-helium atmosphere of this Neptune-like planet should have been blown away long ago, but it's still there, which is very strange. Astronomers also made a graph of planet radius versus orbital period. The y-axis is planet radius. The x-axis is the time it takes for the planet to orbit its star once, the orbital period. From the graph, it's clear that, in the region very close to the star, there are basically only rocky planets with radii 1 to 2 times Earth's. A bit farther out, you start to see large gas giants, and Neptune-like objects are mostly concentrated in even more distant regions. In the near-star region, there is a triangular area where very few Neptune-like objects are found. Astronomers call this area the Neptune Desert, and LTT 9779b is the point marked by a pentagram on that graph. It sits right in the Neptune Desert, one of the very few Neptune-like objects surviving there. Because it's so close to its star, its orbit is tiny, taking only 0.8 days to complete one orbit. That means a year on this planet lasts only 19 hours. At such close range, the surface temperature is naturally very high. Its equilibrium temperature is nearly 2000 Kelvin, about 700 plus degrees Celsius. This temperature is almost comparable to the surface temperature of some red dwarf stars, so astronomers also call it an ultra-hot Neptune. The next question is, under such extreme heat, how can a small gas giant, primarily composed of hydrogen and helium, hold onto its atmosphere? Some scientists speculate it might originally have been a Jupiter-sized gas giant. Later, because it got too close to the star, a large amount of its material was stripped away, leaving it the size of Neptune today. But the problem is, relying solely on stellar wind and intense heating, losing so much mass quickly enough for a giant planet is very difficult, so some think it might have experienced another mode of mass loss called Roche-Lobe overflow. Simply put, Roche-Lobe overflow occurs when a gas planet gets so close to its star that it even enters the star's Roche limit. The minimum distance in TNT celestial body can maintain its structure due to its own gravity. Then, the star's tidal forces pull and inflate the planet's outer gas layers, exceeding the range that the planet's own gravity can bind. This is the Roche-Lobe. Thus, the planet's material is lost in large quantities to the star. The current LTT 9779b might be in transition from a giant planet to a rocky planet, under the combined effects of evaporation caused by stellar radiation and Roche-Lobe overflow caused by tidal forces. But why this transition process is so slow has been puzzling. Until October 2023, there was a breakthrough. An article published in the monthly notices of the Royal Astronomical Society said researchers used the XMM Newton Space Telescope to observe the X-ray emissions of this planet's host star. The results showed that this star is actually much gentler than everyone thought. Its rotation speed is unusually slow, and the intensity of X-rays it releases is only 1/15 that of stars of the same age. Originally thought to be an energetic young lad, it turned out to be a rather feeble scholar. This weak stellar radiation might be one reason why this planet can hold onto its atmosphere. Having solved the atmosphere problem, a new question arises. As an ultra-hot Neptune, how does it have an ultra-high albedo of 80%? Remember, the gas giant with the highest albedo in our solar system, Jupiter, is only 50%. To have such strong reflective power, there must be secrets hidden in its atmosphere. Fortunately, this planet isn't too far from us, only 264 light-years. Astronomers can use space telescopes capable of observing the infrared band and employ transmission spectroscopy, observing spectral changes in starlight as it passes through the planet's atmosphere, to analyze the components of its atmosphere. Subsequently, astronomers used the Spitzer telescope, the Hubble telescope, and the Webb telescope to observe this planet's atmosphere. The results did not disappoint. Besides the expected hydrogen and helium, its atmosphere has an abnormally high metal content. The metallicity proportion of metal elements is hundreds of times that of the Sun. Upon closer analysis of the spectrum, an even more astonishing discovery was made. The clouds in this planet's atmosphere are actually composed of silicates. What are silicates? They are the main components of substances like the rocks, sand, and glass we see every day. Rocky planets like Earth are basically made of silicates. Different types of silicates have different boiling points, generally around 2000 plus degrees Celsius. The boiling point of glass is even lower, only around 1000 plus degrees Celsius. Considering this planet's surface temperature of nearly 2000 Kelvin, the silicates in its atmosphere can indeed be evaporated into gas, forming silicate clouds. But that's not all. Scientists also found titanium components within these clouds. That is to say, the sky above this planet is actually shrouded in titanium silicate clouds. No wonder its reflectivity is so strong. It's equivalent to the entire planet's surface being covered in a metallic mirror. Sunlight comes in, and most of it gets reflected back. We can try to imagine this planet's environment. A huge, scorching hot star hangs in the sky. Surrounding it are rolling clouds of metallic vapor and silicates. When these clouds drift to slightly cooler regions, the metallic titanium within condenses into liquid droplets and falls as rain. But halfway down, it gets re-evaporated into vapor by the high temperatures near the surface. Thus, it evaporates, condenses, falls, and evaporates again, in a perpetual cycle, forming an eternal, never-ending rain of titanium. Finally, let's summarize. This ultra-hot Neptune can exist in the Neptune desert, mainly for three reasons. First, its host star, although young, has exceptionally weak X-ray radiation and not very strong stellar wind, preventing its atmosphere from being blown away rapidly. Second, its atmosphere has a very high metal content. These metallic elements make the atmosphere heavier, easier for gravity to Shufu bind/restrain, and less easily stripped by stellar radiation. Third, the metallic cloud layers in its atmosphere, especially the titanium silicate clouds, provide an ultra-high albedo of 80%, blocking most stellar radiation and preventing the planet from being excessively baked. However, these reasons are still preliminary conclusions. The mysteries surrounding this ultra-hot Neptune are not fully solved yet. In the future, the Webb telescope might conduct more detailed observations of it. Perhaps it can collect more data to help us completely understand why it can survive in the Neptune desert and how its peculiar atmospheric environment actually formed.